Hey class, I hope you're doing well. I feel terrible interrupting you in the midst of such a glorious exam, but alas, we do have class today. I hope that everyone is progressing correctly or progressing well through the exam. So today I wanted to start off with a discussion about unit testing, and then the rest of the lecture we'll go over what the notes have to say regarding graphs. So let's jump to it, and we'll try and keep today's lecture short so that you have plenty of time to continue to work on the exam. And again, if you have any questions, other than what's the answer, please feel free to reach out to me, and I will be happy to help clarify. Okay. Okay, so regarding your exam and unit tests in particular, I wanted to take the opportunity to use 2.1 as an example for the case for unit tests, right? So everyone wants to do well on the exam. Everyone wants to do well once you get out there in the professional world, or once you start pursuing your individual passions. And part of that is making sure that the work that you do is correct, right? So in this case, we're looking for a recurrence relation, so we're looking for something of the form A of n, right? And we don't really know what that looks like yet, but we do know what f of n looks like. So let's define that. Right? So we have some function, f of n, and we'll say that so again, part of a correct definition is limiting the scope of your entries, right, of what it is that you address. So in an algorithmically correct way, we would test all of the edge cases, right? So if n is less than 0, we'll return 0, right? If n is equal to 0, so if the length of our string is 0, then we would return 1, because the empty string has an even number of zeros and that it's 0, so we have a 1 there. And actually, I wouldn't even consider returning 0 as correct here, right? So in this case, we should actually throw an error. And indicate that it's out of bounds. And I think it's good to always print what the actual value is, so we'll use the interpolated string here. Right, so that'll correctly throw our error. Alright, so now on to constructing f. Right. So we need a function for padding leading zeros, so that we can just iterate from 1 through 10 to whatever power it is we're looking for, in order, or sorry, from 0 through 10 to the n minus 1. So let's quickly write our padding function. And so padding takes some num, right? And then it turns it into a string. So num is equal to the string version of that number, right? And this should actually be something like padded, right? So that's our padded string. And then we need another parameter to indicate string length, So while the length of our string is less than string length, the desired string length, then we want to prefix it with a 0. Okay. And then once that condition is satisfied, we'll return that string. Okay. So now that we have that, we will loop through. We'll write our loop. Oh, sorry. So we need the tally, right? This will be the ultimate return value for this function. So the tally is just our counter for the number of values that satisfy this condition. So the first thing we have to do for each integer is get the padded string. So let our string be the padded version of our number. And then for every character, we're going to check if we have an even value, right? So is even. And in this case, even means an even number of zeros. Right? So to start, we have 0 zeros. So it is even, because 0 is an even number. So each time, so if the character at our jth index is equal to 0, then we need to toggle is even, right? So if it's true, then it becomes false, and if it's false, it becomes true, right? And so once we've checked the string, the string of length in, to see whether or not oh, sorry, we should have passed that length in here. So if it's even, once we've gone through the entire string and counted the number of zeros, then we increase our tally, right? And then we return that at the end. So let's see if we've done that correctly. So f of 0 is 1, f of 1 is 9, and that's correct. So for all the strings of length 1, there's 0, which has 1 0, and it's odd. And there's 9 other strings that don't have it, right? So, okay, so it looks like it's behaving correctly. We would get some value for 2 or whatever. So we have our test function, right? So our unit test, right? Typically you would define it differently, right? But here, you know, we'll have it accept a parameter, but whenever you're working on your project, you would typically set up your unit tests as part of a like, especially if you're doing object-oriented programming, you would set up kind of these companion classes. So for every class of code that you write, you would presumably, you know, it ends up not being one-to-one, but you would have a class of unit tests, so a collection of tests that work against that code. Right? So you have your sequence generator, right? In this case, we're going to write a unit test that accepts a function. And then we'll say test passes equals true to start, and then we'll return that. So, sorry. Okay, and so we have how we know it should behave, and we're going to test whether or not the solution we came up with, right, is going to match this. So in this case, we would just define, like, we would test it for a sequence of string lengths. We'll say for up to 5 or something. Test passes if all other tests have passed, and sequence generator here, we'll rename this variable. I really don't like the variable names I've chosen. It's kind of a poor example, but I tend to use the shorthand for these iterators. So if it's equal per value at that length to the function that we've already defined, and all other tests have passed, then it continues to pass, and then we return the result at the end, right? So I will show you it failing, right, because we want to test our unit test first. And this is kind of the spirit of test-driven development, is that you write a unit test and you know the test to be correct, and then you write some failing function, which is really just a function that hasn't been implemented yet, but it compiles, and then you work to make the test pass, right? So you write your criteria for success first, and then your tests will tell you whenever you're completed. And so there are some people that swear by this method. I have always been one of the people that have to go back afterwards and write the tests once I've written the code. And part of it is that if I'm the one, as the developer, if I'm the one defining what it is that I need for this project to be completed, then I tend to feel my way out with the code, and then I test against it to make sure that I got everything, but I kind of do it after the fact. But if you're in some scenario where you have all of your requirements up front, which when you're a junior developer, they're more likely to set you up with something like that, where they tell you exactly what it is they need, then in that case you should write the test first, or you should at least experiment with it to see if it's something that is successful for you, right? So in this case, I'm giving you the test, and then I'm asking you to do the test-driven development. So you have the test, now write the function or the recurrence relation that will satisfy this test, right? So your sequence generator will take in some value, right? Or some string length. And we have this hard-coded value up here, right, for f of n, right? So we know that when n is equal to 1, or sorry, 0, we return 1. And we really don't know anything beyond that. We don't know the degree of the recurrence or anything, right? So for now, we're just going to write it in some other fashion, right? And we'll say that it's the same value over and over again. So that's a recurrence relation. We don't know if it's correct, so let's run our unit test, right? And we have our sequence generator, which is A, and it fails. So our test failed. That's it. That's test-driven development. Now, write your code and test against that. And so I had kind of waffled on whether or not to include this now or to wait until after you'd finish the exam. But I got some questions about whether or not we should consider leading zeros for these strings. And yes, we should. And so I thought, well, okay, in all fairness, I really should clarify that, or it should have been more clear. And so now you know exactly what it is I'm looking for. See what you can do in regards to generating that recurrence relation. Okay. Okay, so now on to graphs. So a graph is a collection of vertices combined with a collection of edges. And so the edges are the line segments that connect two vertices. You cannot have an edge that doesn't connect, to anything. You can't have this bridge to nowhere or whatever, right? So for a graph, the edges always connect two vertices, not necessarily distinct. You can have a loop where you're connecting the same edge to itself, right? And throughout all of this, right, as I speak about graphs, I want you to keep in mind both like highway systems, right, like where the edges are the roads and the vertices would be the cities or the destinations or whatever. So systems of road or transit or whatever, and networks where the computers would be the vertices and the connectivity to the network, either the wireless connection or an actual physical cable connecting a computer to some other device like a switch or a hub or a router would represent the edges, right? And so in this case, if you think about the cable, then any place that the cable connects to would be a vertex, right? And so if you had a computer with a cable, connected to its network card, but it doesn't connect to anything else, so we wouldn't count that as an edge, right? So it has to connect, right? And so in the case of networks, there actually is a loopback interface. It's 127.0.0.1. So if you that's localhost. It's an alias for localhost, and so every machine defines that as the loopback interface. And so even though there's not a physical cable, there's a logical connection that allows each machine to access itself over a network that never actually goes out onto the network. It just stays on the computer, right? So anyway, okay, so networks of transit, like roads and highway systems or whatever, or computer networks. Okay. Simple graph. Okay. A simple graph is just one where you don't have repeated connections between vertices. So it doesn't mean that they can't travel through some other path, right? They can still be path connected by multiple routes, and we'll get to that later. But how I was saying, you can think about them as you can think about graphs as being computer networks. Well, this is the same thing as saying that you don't have two Cat5 cables running from the same computer to the router. So that's a simple graph. It's what you would think of when you think of a graph in these other terms. Right? Okay. So if you do allow that redundancy, where multiple edges can connect to the same graph, or the same two vertices, then that's called a multigraph. Okay. We've discussed loops kind of already, and so if an edge connects a vertex to itself, then it's called a loop. Right? Let's see. Okay, a directed graph is a set of vertices that have a source and a destination, or an initial vertex and a terminal vertex. And so in this case, the source and the destination, the order matters. Okay. Okay, adjacency just means that they are connected directly. So two machines in a computer network would be considered adjacent, not if they connect to the same router, but if there's like a crossover cable connecting the machines directly, or your computer is adjacent to the router, and so it's something that can be reached with one hop in terms of computer networks. Or in terms of roads, the cities are adjacent if there's no cities in between, right? If there's no other vertices that are splitting it up. Okay, and so this is a definition for the neighborhood of a vertex, and so it's everything that is directly connected to that vertex, and so so in the context of roads and highway systems or whatever, the neighboring cities would be the ones that are directly accessible by highway. So it's all of the adjacent cities. Okay. Okay. So the degree of this is a term for the vertex itself, right? And this is in an undirected graph. The degree is just the number of edges that connect to it. So it gets a little confusing if you have a loop, right? So if you have a loop, then it leaves and it comes back in, right? So it counts as degree 2. Every loop adds a degree of 2, but every other edge that is non-loopy, right, an edge that goes somewhere else, the edges themselves contribute 2 total degrees to the graph, one at the source and one at the destination, but it's undirected, right? So there is no source or destination. There's just the 2 points that it connects. Right? So the degree is a property of the vertex, and for every line segment that comes into it in an undirected graph, so there's no arrows or anything in this, counts as a degree of 1. And again, loops would contribute to. A vertex is called isolated if it has degree 0. So if it's not connected at all, you can think of an isolated machine or an isolated village, a place where that is inhabited but has no roads connecting it to the rest of society. So that concept translates very well. Handshaking theorem. Okay. So this is kind of what I was trying to say earlier whenever I was talking about degree. So if you add up the degrees of all of the vertices, then it'll be twice the number of edges. So an edge, you can think of it as having a head or a tail, or as having 2 ends, or whatever, but it plugs in to 2 different, or possibly the same vertex, but it plugs in at 2 points every time you have an edge. So all this theorem says is that each time you add an edge, it'll contribute an even number to the sum of all of the degrees, and it's because the edge is always connecting to 2 points in order to be part of the graph. So this, it's a pretty simple statement, even though it's presented as a theorem. An undirected graph has an even number of vertices of odd degree. Okay. So what are we saying here? So if you have, like, imagine a graph with just two vertices and one edge. Okay. So the edge connects vertex A to vertex B, and so you have two vertices, each of degree 1. Okay. So let's add one more vertex. Let's add vertex C to this scenario and connect B to C. So now vertex A has degree 1, and it's the edge. It's formed by the edge connecting it to vertex B. Vertex B has degree 2 because it's connected by one edge to vertex A and by another edge to vertex C. And so vertex C has degree 1. So there are two. So now even with three vertices, there's two vertices with an odd degree. So with degree 1. And so it's that's essentially all that it's saying, is that you can take a vertex with odd degree and make it even by adding some other edge, but by doing so you are either making some other vertex of odd degree now even, or you're passing the buck, right? You're kicking the can down the road. So if the vertex it connects to was previously odd, it's now even, and so you've reduced the number of vertices with odd degree by 2, which keeps it even, or you've transferred something that was even to now be odd, so that you've had no net change. You made this vertex that had an odd degree even, and this one that had an even degree odd, so that in terms of this statement, nothing has really changed. And so if you play the game, right, and you try to come up with a graph where one vertex has, or where an odd number of vertices have odd degree, you'll see that it can't be done, and it's because the edges are always contributing a sum of 2 degrees to the graph, right? Because it has 2 terminal ends, and so you can't break this rule, right? So it's an interesting thing to think about. But okay, so now back to terminology. So if we have a directed graph with U and V, then we say U is adjacent to V because you can go from U to V, right? But it's directed, right? So V is not necessarily adjacent to U because it's not accessible through this edge right here. It's adjacent from U in that it receives, it receives an edge sourced from U. So U is called the initial vertex, and V is called the terminal vertex or the end vertex. Okay, and then in a loop, the initial and the terminal are the same vertex. Okay, so a complete graph with n vertices and denoted Kn is a simple graph that contains exactly one edge between each pair of distinct vertices. So if you have a graph of 5 vertices, then each vertex would have an edge that connected it to every one of the other 4 vertices, right? And so it's a pentagon essentially, if you position it that way, with the edges running to from every vertex to every other vertex, and it gets kind of cluttered pretty quickly, but that's a complete graph. Okay, so it's a pretty simple concept. It's the loudest simple graph that you can have in terms of if you were to draw it on a whiteboard. Okay, a cycle is a path that visits each node of a graph once and terminates with the origin. So, like, okay, so if you consider like a paper route or something, you all might be too young to even know what a paper route is. I don't know. Then it's just, you start at your house, and then you ride to every one of your customers, delivering your paper. And you try not to ride past the same house twice, because that's wasted energy, right? Like, you want to visit each one of your destinations exactly once, and not revisit anything. Everything feeds into the next thing. So that's a cycle. This concept that you're not revisiting anything, and so it's not always guaranteed to exist, right? So if you have a bike route that takes you to the end of a cul-de-sac, well, you can't help but reuse that same road. So in that case, you can't achieve this, but sometimes you can, right? And it has this concept of minimalism to it, and that everything is visited once and no more than once. And so cycles, because of that minimal property that they have, are interesting things to study. Okay, bipartite. Okay, I'm gonna have to draw something for you for this to make sense. But first, let's go over the definition, and then we'll talk about it. So you have these two disjoint sets. You have a graph. It's some simple graph, so that you don't have the redundancy of edges connecting the same vertices, whatever, right? But it splits in that you can kind of separate it out into these groupings, where and you call these groupings V1 and V2, so the first set of vertices and the second set of vertices, that connect to from group 1 to group 2, but never within the same group, right? And so you can think of this as, I guess the best example really is, okay, if at a dance, you have all of the members of class A line up on one wall, and all of the members of class B line up on the other wall, and you insist that no one from class A dances with anyone else that's in their class, and no one from class B dances with anyone else that's in their own class, right? So you have this fusion of networks where they are connected. People come together and dance, but this simple rule that, okay, we were able to organize them into these two groups without having any of the edges or any of the vertices, the nodes, or people, if you want to call them that in this, then that are partnered up in this way. They're separated, and so that would be an example of a bipartite. But let me draw one for you as well. Okay, so this will be one with just 6 nodes. So you have A, C, and E. And then B, D, and F. And you're not even guaranteed that they have the same number in both, right? So we can get rid of F, and it would still be an example of a bipartite graph. And so we make no promise that it connects to every node in the other group, right? We don't really know. But the only guarantee is that nothing from V1 is connecting to anything else in V1, and nothing from V2 is connecting to anything else in V2. So in the example of the dance, You can separate them up into two classes along the walls, and then they can meet in the middle essentially, but no one is allowed to dance with anyone from their own class, and so that's an example of a bipartite graph. Okay. Subgraph. Okay, so this is essentially always there. You can always take some smaller set of vertices or some smaller set of edges. As long as there's more than one vertex and more than one edge, you can always trim it down. And so graphs are so loosely defined. It's just vertices and edges. Right? So if you reduce this set, right, and you reduce this set, and so if you take away a vertex, then you have to take away any edges that are associated to it. Well, then you would have a subgraph. So for a proper subgraph, at least one edge and or one node must be removed. Yeah, it says exactly that. Right? So if you remove a node, then you have to take away the edges, right? So generating a subgraph is really easy. Okay, so isomorphisms. Two graphs are said to be isomorphic if there exists a one-to-one correspondence between their vertex sets, which preserves the edges. So this is the definition. I think later we'll come up with a theory on isomorphisms, but this is the definition of an isomorphism. And so basically it's just a relabeling, right? So you have V1 and V2 and U1 and U2. Then any edge connecting V1 to V2 has an analog which also connects U1 to U2. Okay, so if you think about instead of computers on a network, if we were to think about people, right? So everyone, if we assume everyone has a computer, then we identify the computer not by its IP address or necessarily anything else, but by the human user associated to it, then it's a little easier to think about, right? So then the computer is, it is something that's available to that person, but the person is kind of at the end, right? So, but the computer is what's on the network. So if we replace if everyone has a desktop computer, and then we take that away and we replace it with a laptop for every person that's on the network, it's still the same network, right? Like possibly new IP addresses, local IP addresses for everyone, maybe, but the network is essentially unchanged. All of the edges that are connecting these new vertices are, it's still the same thing. Every endpoint has changed, but the network is exactly the same. We just traded desktops for laptops. And as far as like a study of the network goes, we've just relabeled the endpoint. So now instead of calling everything desktop 1, desktop 2, whatever, we're now calling it laptop 1, laptop 2. And so isomorphisms, this is just the word that we use to say that this object, a graph, it's not equal in the sense that it's exactly the same, but it satisfies a lot of properties of equality, in that the structure of the network is preserved. So it's exactly the same in that sense as the previous network. All we've done is kind of shuffle the labels a little bit, but the network is preserved. And so this is the formal definition for how we can say that idea, right? That, well, you haven't really changed anything. It's isomorphic to what you had before. Okay. So an adjacency matrix is this thing, right? It's just the matrix representation of a graph, right? So this is an example of a graph, and A connects to B, and because it's undirected, B connects to A, right? So we have that represented here from A to B, and from B to A, right? So source, destination. Then you can construct a matrix from any graph. Right? And even if you had a multi-graph where you have redundancy, you can still represent that concept and say, okay, well, if there's a second cable connecting A to D, then from A to D, instead of there being a 1 there, you'd put a 2, whatever, right? And so adjacency matrices are a really computationally friendly way to represent a graph. So yeah, you have vertices, you have edges, now you have a matrix derived from that, right? So take a moment to study this, right? This concept, it's pretty simple. It's just a matter of getting familiar with it. Yeah, it'll be on your next, it'll either be on your homework and or your exam. So it's worth a minute to glance at it. Okay. So this is a more formal definition of an adjacency matrix, right? So row I, column J is 1 if there's an edge connecting it, right? So that's what this says. And it's 0 otherwise, right? So that's all of this is saying. An incidence matrix, okay, it's similar to an adjacency matrix, but instead of going from vertex to vertex, you have vertex to edges, right? So an edge always has a source and a destination, or in an undirected graph, it has 2 terminal ends. So in this case, where the edges are columns, every column will have 2 1s, right? It'll have, one end of the terminal, or one terminal end of the edge, and the other terminal end of the edge, right? So incidence matrices, they're just another way to represent the network, right? So instead of having all of the rows and all of the columns be the vertices, you now have the rows as the vertices and the columns as the edges. But I prefer the adjacency matrix, but this is another way to represent a graph or a network. Okay. So we return to the concept of isomorphism, but this time to describe something that's non-isomorphic, right? So okay, and the function that kind of does that relabeling, it relabels the vertices and relabels the edges, is an isomorphism. And then if the graphs are not isomorphic, then it's called they're called non-isomorphic. Right? Okay. A path. So before we had a cycle where you ended up like the paper route, right? Where you ended up back where you started. But a path is more of a question of connected, right? So in terms of a network, it's just the question of can I send a file to this other machine? Is there a path that allows us to get there? And so that's essentially all that we're asking for, is are we connected through some route? And in terms of roads or whatever, is there some route that I can drive from where I live to where they live, right? If yes, then there is a path, and if not, then no. Okay, so circuit or cycle, we've already discussed that, right? It starts and ends at the same vertex. It's called simple if we don't reuse the same edge, right? So if there's no cul-de-sacs, essentially, then you have a simple circuit or a simple cycle. Connected, an undirected graph is called connected if there's a path between every pair of distinct vertices of the graph. I think this is perfect for for the concept of networks, right? So your network is connected if every machine on your network can communicate with the router or the default gateway or whatever. And if not, then it's disconnected, or I would say that you have a vertex or a node that is disconnected from the rest of the graph. Okay. So this is a theorem. There's a simple path between every pair of distinct vertices of a connected undirected graph. Yeah, so where you're not having to travel back and forth, right? And if you think of this in terms of a road, then basically this is saying that if you're on the same network of roads, then you can drive there without having to go to retrace your steps, basically, right? Like, I can drive to Fort Worth without driving to Oklahoma City first. Like, I can go straight there because we're connected. And so the statement is not particularly profound in that sense, right? But in terms of a network, it is more of an important concept. So this is essentially saying that the same packet of information shouldn't travel through the same the same router, the same whatever, more than once. Like it shouldn't be circling around forever. It should be able to get there if that path exists, if that device is connected. And so that's essentially all that we're saying. So you don't have to revisit any vertices or any edges or anything like that. Like, you should be able to just go in kind of a direct way. Okay. All right, connected components. So this is more of like a case. So if we're discussing like networks, like computer networks, then imagine you had a classroom where, so again, two classrooms, Class A and Class B, where all of the computers are connected by a switch to the other computers in their classroom, right? But they're not connected to the internet itself, right? So you have a LAN party or something, you're playing some game, but it's only accessible to your classroom. So then, in this case, where we have two classrooms that are each connected within themselves to this switch, then we have two connected components, right? So they're connected to each other, and in that sense, but they're not, they're connected to themselves, but they're not connected to each other in that sense. So, there would be two separate connected components. So connected subgraph of G, that is not a proper subgraph of another, right? So if we ran a line connecting, if we connected the two switches so that the networks could suddenly see each other, then there would be one connected component. So it would all be one happy network. But if we remove that, then we have two, if that makes sense, right? So, okay. So then cut vertices, right? So in this LAN party example that we were just using with the two classrooms, so the Cat5 cable that we ran from Class A to Class B would be an example of the of a cut edge, right? So the cables are the edges, so, or the bridge, right? So if we remove this one edge, this one cable, then we no longer have this larger network. We're now dealing with two distinct connected components, so that cannot see each other. And so the vertices, in this case, where we have the LAN party, if instead of connecting them directly, like from one switch to the other, if we had some router or some gateway that each fed into, right? So they're classrooms. Let's say that they're all connected to each other on a switch, and then there's a cable running from the switch that connects to the school's router, so something that allows access to the outside world. And then also, like, the router allows the classrooms to see each other. If we remove that router, then all of a sudden the classrooms cannot communicate, outside of, like, Class A can only communicate to Class A and Class B can only communicate to Class B, right? So these two distinct connected components. So the router in this example, which is connecting the classrooms, and then it's also allowing them access outside, would be an example of a cut vertex. Okay, so you remove it and things start breaking down, right? So it's this critical point, or they call it an articulation point. Okay. So we'll end with this one. I want to keep this one short. So non-separable graphs are connected graphs without cut vertices. So this is an example of the wide area network, right? Like, you have your internet service providers, and at that level, these ISPs that are allowing everyone access to the internet, they strive for redundancy. So not just multiple cables running between them, but a larger network where they connect to each other, more than just like in a hierarchical way. They're kind of trying to connect to as many of each other as they can, so that even if an earthquake swallows up one ISP, it doesn't harm the network. The network can kind of heal itself by just not sending traffic that way anymore. And so there is no cut vertex. There's no critical point where you can bring down the internet, right? And so non-separable graphs are what we strive for in the larger wider area network. Okay, so that'll be it for now. We'll come back and we'll finish up graphs, and if we move fast enough, we'll talk about trees next time. But I had promised that we'll focus on coding more during this middle third of the semester. So if we do reach the end of this, then we'll spend a little bit of time discussing Dijkstra's algorithm on shortest paths. So all right, good luck with the exam. Have a great weekend, everyone, and we'll meet again on Tuesday.